try. So he's saying try and calculate the E naught cell for this reaction. So we're going to try and do that. You see, just 1 second. So okay, we're going to try and do that for this particular cell. I'm just going to look at this very, very carefully. The first thing is they've already made the reaction for you, okay? So you don't have to do the who gains electrons, who loses electrons. Everything has already been done. So you just have to identify what the electrodes are. So there's clearly one electrode which involves the I minus 1, I2. So it's I remember that it's 2I minus 1. No, it's actually I2 plus 2 electrons in the data booklet, and in equilibrium with 2I minus 1. So I'm going to go and have a look, and the E naught is also given at 0.54 volts. And the other electrode, if you look at it carefully, that's your copper 2 plus, and there's copper 1 plus. I mean, this is copper 1 plus. So there's a copper 2 plus, copper 1 plus electrode that has an E naught of, it's probably this one. So it's your copper 2 plus, copper 1 plus electrode, and it has a value of 0.15 volts. So they've already made the reaction for us. I mean, the overall reaction has already been made. So I'm doing the reverse now. So plus 1 electron in equilibrium with copper 1 plus, and the E naught that they had given in the booklet was 0.15 volts. So I have these values with me. Now I'm just going to follow what he's doing, right? Because he's already made the reaction. So copper 2 plus changes into copper 1 plus. So this one is going in the forward direction, right? This is the part that is getting reduced. And the other one, you have your I minus 1, and it is getting oxidized to I2. So that's I minus 1 changing into I2. That's the part that's getting oxidized. Now, I have a simple question. Should this reaction happen this way, or is there something wrong with this, the way he's describing it? Who's supposed to gain electrons? Anyone?
The one with the higher potential, so iodine should be the one gaining electron.
Copper should gain electrons.
The one with the higher potential. Higher potential gains electrons. So it should have been iodine, right? Abdullah, is this clear?
Yeah.
Acha, so the thing is, what he's doing is completely wrong. Because what we've studied is that the reaction is not going to happen this way. This is not a feasible reaction. It's not going to happen this way, because the higher potential is the one that's supposed to get reduced. It's the one that's going to gain electrons, and the lower potential is the one that's supposed to lose electrons. But the reaction is happening in a completely different way. Anyway, so I'm just going to follow what he's doing. He stated that copper 2 plus changes into copper 1 plus, so I've done that. He stated that I minus 1 changes into I2, and I've done that. And I know that that's not going to happen. So he's asking us to calculate the E naught cell. The E naught cell is reduction potential, which is this one. It's 0.15 minus oxidation potential, which is 0.54. And I get, what do I get? I get minus 0.39, right?
Yes.
So I'm getting minus 0.39 volts. Now this negative voltage indicates that what he did was completely wrong, and the reaction is not feasible. So he's saying predict that the reaction, explain how the value of the E naught cell calculated in one predicts that the reaction is not likely to happen because the E naught cell is coming out to be less than 0. What that actually means is a negative voltage, when it comes out to, when you get a negative voltage, that basically indicates that the direction in which he was suggesting the reaction would go, it's going to go in the complete opposite direction. So is that the negative voltage indicates that the electrons are going to flow in in a complete opposite direction to what he's stated over here. Is that clear? TK, is this clear to everyone? Rubena, is this clear? Shafak?
Yeah.
Yes, sir.
Now, The other part is, so we know that this was completely like this was complete nonsense. The reaction was not supposed to happen this way. Now, but always remember, E naught cell is reduction potential minus oxidation potential. Now, in an experiment, a solution of I minus 1 is added to a solution of copper 2 plus, and a reaction does occur. So he's saying that I minus 1 and copper 2 plus are added, and you actually get a reaction, and there is a reaction that's happening, right? So the concentration, now a reaction does occur. Now, the reason the reaction might occur in reality is that in the real world, you don't use standard conditions. So he's saying the concentration of copper 2 plus remaining in the solution is 1 mole per dm cube, and the concentration of copper plus 1 in a saturated solution of copper I is 1.3 times 10 power minus 6 mole per dm cube. So it's a non-standard solution. Use the Nernst equation to calculate the electrode potential E for the copper 2 plus copper plus half cell in this experiment. So what's the Nernst equation? First thing, you have the copper 2 plus, copper 1 plus electrode. And the E naught for that was 0.15 volts, right? So the first thing is, explain to me. In reality, the reaction that he's doing, the copper 2 plus concentration is 1 mole per dm cube, so that's fine, nothing wrong with that. That is standard concentration. The concentration of copper plus 1 is 1.3 times 10 power minus 6. So it's coming out to be. Based on, by looking at the concentration, where do you think the equilibrium would shift? Forward or backward?
Backward.
If forward, if you decrease the concentration, remember it's 1.3 times 10 power minus 6. If Abdullah, is this clear?
Yeah.
So you're decreasing concentration, the equilibrium will try to make more of it. It's going to try and increase concentration. And whenever equilibrium shift forward, the potential increases. Why does it increase? Because all of a sudden copper 2 plus has started gaining electrons, and your electrode, the platinum electrode that you've added, it's going to become even more electron deficient because all the electrons would be taken up by copper 2 plus, and uh, the electrode would become even more positively charged. So whenever the equilibrium shifts forward, the potential always increases, it becomes more positive. And whenever the equilibrium shifts backwards and it produces more electrons, the potential decreases, it becomes more negative. In this case, it increases. Okay, Aruba, Shafak, is this clear?
Yeah.
So now the question is, he's asking us to use the Nernst equation and calculate the electrode potential. So I'm going to use the Nernst equation, which was that you had to remember this. It was E naught plus 0.059 over Z, and it's log of the substance that's getting oxidized. Oxidized species is the one that's on the left side, and the substance that has been reduced. Reduced species on the right side. So I'm going to use this. The old potential is 0.15 volts. So I'm going to use 0.15 volts plus 0.059, and that should be divided by 1. That's the number of electrons, Z. Log of oxide species has a concentration of 1. So it's log of oxide species, which has a concentration of 1, divided by reduced species, the one that's on the right side. So that's 1.3 times 10 power minus 6. Can anyone solve this and tell me what the new potential is?
So the E naught value is 0.5, right? 0.15.
Yes, it's
0.15.
हाँ तो बता एक सेकंड होल्ड
No,
करें
that's the E naught value, right? The old one.
एक सेकंड होल्ड करो सारे ठीक है
Okay.
Sorry. Shafak, what were you saying? Hello?
So I was asking for like the previous E0 cell value is 0.15, right?
It's 0.15, yes.
Yeah, okay, so it's 0.15 plus 0.059 upon 2 and log of the oxidizer upon reduced, right?
Yes, but not divided by 2, it's divided by 1.
Oh, it's not 0.059 divided by 2, it's divided by 1.
0.059 divided by
Yeah.
1.
Oh, okay.
Z is the number of electrons. The number of electrons, that's
Oh,
1.
okay.
So,
Because it looks like a 2, that's what I was asking. If it's a 2 or if it's a Z.
I said this one. This is Z.
Yeah.
I said this
Oh,
is Z.
okay.
So did anyone do this?
Yes, sir, I did it, but I don't think my answer is right. I got minus 1.2.
No, that's not right. Because we just figured out that it should increase, right?
Yeah, yeah.
Oh, the answer that I'm getting is 0.497. So like 0.50, you can write it as.
Okay, so you're
Yeah.
getting 0.5. That's right. I mean, let's be more correct about this. How many significant figures you should use? I think your number would round off to this. I say anyway. So
Wait, should I write as 0.500 or 0.50?
0.50, because what value did you use? The previous E0 was 2 decimal places, right?
Yeah.
So I mean, that means 0.15. You don't know what the next digit is. So even over here, you won't know so it's going to be 2 significant figures. So it's going to be 0.50 volts, right? Is that clear?
Yeah.
You can't be more accurate than the accuracy at the start. So anyway, so you're getting 0.50 volts, and that makes sense because it's going to increase, right? So the thing is that if you change the concentration, why is the reaction happening? I mean, we previously suggested that the reaction is not going to happen, right? Because the voltage was 0.15, right? But if it becomes 0.5, then the potential is drifting towards positive side now. zero point 0.5 minus 0.54 is very less negative, right? And even the iodine in reality is going to vary because iodine is sparingly soluble. So there's going to be very less I2. The concentration of I2 in solution is going to be very less. If it's very less, the equilibrium over here is also going to shift to the left. And if it shifts to the left, this is going to become lower. So if this becomes 0.5 and this sort of increases and it becomes so it decreases and becomes, let's say, 0.45, then what you're going to get is you're going to get a positive value and the reaction will happen. Is this point clear?
Yes.
Okay, because under standard conditions, the reaction is not feasible because this is not the higher potential. But under non-standard conditions, this kind of becomes the higher potential. It becomes zero point 0.5. And that one would probably be slightly lesser because I2 is sparingly soluble. So equilibrium would shift to the left. It's going to become more negative. So this one would become lower. This one would become higher. And eventually this would become higher than the first one, so it's going to go forward, this one is going to go backwards, and the reaction is going to take place, which is why in the experiment a reaction does occur because you're using non-standard conditions. So is this clear?
Yes, sir.
Abdullah, is this clear?
Yes, sir.
Now the other one is, now he's saying that copper 1 chloride is also sparingly soluble in water, suggests why the following reaction does not occur. So it's the same reaction except that this time we've got everything is the same. It's the same copper 2 plus copper 1 plus, and the E naught is 0. Under standard conditions is 0.15 volts, and the other one is your uh, Cl minus 1 Cl2 electrode, and the E naught for that is 1.36 volts. So this reaction is kind of the same as the first one. It's I2. Instead of I2, you have Cl2. Now, in this case, he's saying that even though they have similar solubilities, so copper 2 plus, copper 1 plus would be very insoluble. So copper 1 plus concentration is going to be very low. The equilibrium is going to shift forward. This is not going to be 0.15. It's going to be a high value. Let's make it 0.6 volts, right? Just like the previous case, it became 0.5 volts. I'm even increasing it further. Now, even if the potential increases, the difference between the two potentials is very high. No matter how much this potential increases, it still is the lower potential. And the reaction is not going to go forward because it's the higher potential that gains electrons. So this forward reaction is not going to happen. Copper 2 plus is not going to change into copper 1 plus. Why? Because even if the potential changes, it still remains the lower potential. Is this clear? Ruben, is this clear? Aruba, is this clear?
Yes, sir.
Sir, how do you change the potential again from the way that you,
Nee, over
how do you
here,
change it?
do you have this concept that if the equilibrium shifts for, I mean, this equilibrium is achieved at under standard conditions, right?
Yeah.
If the equilibrium shifts forward, it gains electrons and it becomes more positive. Do you have a
Yeah.
concept for that?
Yeah.
And vice versa, if the equilibrium shifts backward, electrons are produced and it becomes more negative, right? So the electrode becomes more negative. So the point is, I mean, this 0.6 is a hypothetical value. I just took a value 0.6. It could be, I mean, you could take 0.5. I'm just for the purpose of understanding. Is that clear?
Yeah, but why are you changing the values? Like, what?
Because they said copper 1 chloride is sparingly soluble. That means the concentration of copper 1 plus is going to be less, right?
Okay, that's why it's become dissolved in the water.
So copper 1 plus is going to be very less. And if it's very less, where would the equilibrium shift? It's going to try and make more of it, right? Is that clear?
Yeah, that's good.
And if the equilibrium shifts forward, the potential should increase, right? It's just like in the previous case.
Okay.
Okay. So difference between, you're going to code the two electrodes and you're going to write that the difference between the two electrodes, electrode potentials, is large, and E naught cell would still be negative. It's not going to turn positive. It's still going to be negative. So I'm just going to do a few more examples. Just let's try and do a few examples. Like I have a reaction, and the reaction is between. Let's do. Let's take two equations which are kind of similar, having similar potentials. So let's take the Cr3 plus, and let me take. Okay, let's take the Cr3 plus, Cr2 plus electrode. Cr2 plus, right? And this one is minus 0.41 volts. And I'm going to take another electrode, and that electrode is, this is my, this wave was the Cr3 plus minus 0.41. I'm going to take the Fe2 plus Fe electrode, right? Which is 0.44. And Fe electrode, right? Now tell me, if these two were to react together, who's going to gain electrons, who's going to lose electrons under standard conditions? Which one is the higher potential? It's the first one, right? This is the one that's going to gain electrons, and this one is the lower one. This is the one that's going to lose electrons. Is that clear?
Yeah.
And your E naught cell is going to come out to be positive because reduction potential, so it's minus 0.41. minus the oxidation potential, which is minus 0.44. So if you do that, it comes out to be, I think, positive 0.03. So that's feasible. It's coming out to be positive. TK, is this clear? Abdullah, is this clear?
Yes, sir.
Yes.
So now all of a sudden, what I do is that I decrease CR3 plus concentration. Now let's try and do everything again. TK, forget which one was the higher, which one is the lower one. So all of a sudden what I've done is I've decreased the quantity of CR3 plus in the solution. Where would this equilibrium shift?
Back. I
So
guess yeah.
so it's going to shift backwards, right? It's going to try and make more CR3 plus. So it's going to become more negative, right? So instead of minus 0.41, let's say it becomes minus 0.50 volts, right? Abdullah, is this clear?
Yeah.
Anyway, so forget this arrow for now. So the point is, your CR3 plus concentration, you're decreasing the CR3 plus concentration has made one of the electrodes more negative. Now, which one is the higher potential? Now, this is no longer the higher potential because this is the higher potential relatively now. So if I were to use the same reaction, my E0 cell is now going to come out to be negative because the higher one is more negative now, minus 0.50, minus the lower one, which is minus 0.44. And this now comes out to be negative 0.06, which means it's not feasible because this is not the higher potential. The higher potential is the one that gains electrons. So this should be gaining electrons. So now the reaction is not going to work. So is this clear?
Yeah.
Aruba, is this clear? Shafak? Lubana, is this clear?
Yes, sir.
Yes.
So just remember that changing potentials changing the concentration of reactants and products in an electrode will have an effect on the E0 cell. Maybe the reaction becomes more feasible, maybe the reaction becomes less feasible. So let's try and do this one now. You've got the reduction of chlorate 5 ion ClO3 minus 1 where SO2 forms chlorine dioxide and sulfate ions as the only product. So these two are reacting together, ClO3 minus 1 with SO2, and it produces ClO2 plus SO4 2 minus. So that's the reaction that's happening. Construct an equation for the reaction. So what you have to do is you have to make a balanced equation. Now a redox reaction is only balanced if the number of electrons gained and lost are equal. So what's the oxidation state of Cl over here?
-1. I mean,
That's
Cl
fine.
ka O3.
Sorry. Yeah, of Cl. Can anyone calculate what's the charge on Cl?
+5.
He gets +5. What's sulfur over here? What's the charge on sulfur?
+4.
So that's +4. ClO2 is also going to be +4. And you've got sulfur over here, which is +6, right? So remember, in a redox reaction, the number of electrons gained and lost must be equal. So this goes from +5 to +4, which means what happened to it? Did it gain electrons, lose electrons?
Gained electron.
And it gained 1 electron. It got reduced. Okay? Whenever charge reduces, that's reduction. And this went from +4 to +6. So that means it got oxidized. It lost 2 electrons, right? Now, the number of electrons gained and lost, they must be equal. You have to make them equal. So I need to multiply Cl by 2. Because if I have 2 Cls, the number of electrons gained and lost are going to become equal. Is this clear?
Yes, sir.
Yes, sir.
So remember how to balance. Redox reactions, whenever you have a redox reaction, the number of electrons gained and lost, they always have to be balanced. So, for example, if I make a kind of a simpler, uh, so if I make a simpler equation, and I've got Na reacting with Al3 plus, and the product is Al and Na plus 1. Now, atomized, the equation looks balanced, but it's not balanced. The number of electrons gained and lost are not equal. So Na goes from Na to Na plus 1. That means it lost one electron, right? And Al went from Al3 plus to 3 plus, Al3 plus to Al. That means it gained 3 electrons. So I need to multiply Na by 3. So there should be 3 sodiums. And then the number of electrons gained and lost would become equal. So remember this, whenever you have a redox equation, the balancing is supposed to be done this way. Electrons gained and lost must be equal. What's a disproportionation reaction?
Where the oxidation and the reduction both occur at the same element.
Okay, that's fine. That's what you're going to write. So it's saying and explain the same thing using the reaction. So who's getting oxidized? Who's getting reduced? Like it's the same element, but which one? In this equation, what's the charge on Cl initially over here,
+4.
and over here it's going to be +3, and over here it's going to be +5.
Yeah.
Okay. So that means it's going from +4 to +3. That's reduction that's happening, and it's going from +4 to +5. That's something oxidation that's happening. So what is meant by the term disproportionation? You're going to use this. You're going to say that it's the same element getting oxidized and reduced. So Cl goes from +4 to +3 and also goes from +4 to +5 and gets oxidized. And he's saying reduce the ionic half equations. Now again, we know how to make the full equation. You're not supposed to do the opposite. So let's say so basically this one is a combination of two reactions. There's an oxidation reaction and there's a reduction reaction. So oxidation, Cl goes from +4 to, I think, +5, right? That's oxidation. So it goes from ClO2 to ClO3, right? -1. Goes from +4 to +5. That means it's a loss of 1 electron. So that's 1 electron being lost. Is that clear?
Yeah.
So we have to reduce the half equations. One of them is the oxidation equation. What about the reduction equation? The reduction equation would be, again, the starting point is ClO2. And ClO2 goes from +4 to +3. So that's ClO2 -1, right? And it's gaining 1 electron. Is this clear?
Yeah.
Except for this one thing wrong with it. I mean, it's almost clear. It's almost 80% is right. There's some missing things in it. There's nothing wrong with the reduction equation because it's completely balanced. 1Cl, 1Cl, 1O2, 1O2. Gaining 1 electron, that's fine because it's +4. This is +3. So everything in the reduction equation is fine. The oxidation equation is not fine. Why? Because you've got ClO2, over here you have ClO3. So you're going to add the missing things like what's missing, because the two equations should add up to give you this equation. So what's missing on the left side? That's two OH ions. So I'm going to put in the two OH ions over here because I mean, this equation had nothing wrong. It was completely balanced. This equation is still not balanced. So I'm going to put in the two OH ions over here, and I've got water molecules over here as well. So on the right side, I'm going to add the water molecule. Is this equation looking balanced now? The first one.
Yes.
Okay, because remember the two equations must add up to give you this. So the electrons are balanced, plus 4 to plus 5. The oxygens are balanced, that's 2 and 2 over here, that's 4, 3 and 1 oxygen over here, that's 4 as well. The hydrogens are balanced, there are 2 hydrogens and the 2 hydrogens, that's completely balanced now. So is this clear that the same equation is now split into two half equations?
Yes. Yes.
Okay. So next one is you've got a lithium iodine electrochemical cell that can be used to generate electricity for a heart pacemaker. A cell consists of lithium electrode and inert electrode immersed in body fluids. When current flows, lithium is oxidized and iodine is reduced. So this is what's happening. There's lithium. So there's a reaction that's happening between lithium and iodine. So let's see what's the reaction. Iodine is I2 plus 2 electrons. So I'm going to pick the 2 electrodes from the data booklet. This one is 0.54 volts. And in the data booklet, you're going to have, you will have, that's your iodine, that's the lithium right next to it. It's minus 3.04. So that one is minus 3.04 volts. I said, anyways, he said use the data booklet to write half equations for the reaction taking place at the two. So lithium is oxidized. So I'm just going to follow that. And iodine is reduced. So this is what's happening. So he's saying write the half equations. You're not going to write the reversible reaction. You're going to write lithium changing into lithium plus one electron. And you're not going to write the reversible reaction. You're going to write iodine gaining 2 electrons to form 2i minus 1. Is that clear?
Yeah.
Yes, sir.
And all batteries, all cells, etc. Remember, uh, remember this, that everything is going electric now, from cars to pretty much power generation. Everything is going solar or wind power, or everything is changing into electric. So we're in 10 years, the world would probably fossil fuels would be a thing of the past. So countries are really working hard and they're trying to figure out. I mean, this is what a cell is. It's one substance producing electrons, the other one gaining electrons. So the electrons are driven through the circuit. One side there's going to be an electrode that would be constantly producing electrons. The other side there would be something that would be constantly gaining electrons. So your lithium really likes to lose electrons. It's minus 3.04 volts. So there's a race towards obtaining as many minerals as possible, because batteries are, I mean, there's huge investments going on in batteries. So you should have some idea of how cells work. We know everything that we constructed so far, that's a cell. But remember, these highly electropositive or the substances with very low potentials, they are very useful in batteries. Uh, so these elements are really, I mean, lithium batteries are kind of like, these days lithium batteries are very popular. So you have to construct the overall equation. To construct the overall equation, you would have to make the number of electrons equal. So multiply the first one by 2, add up the reactant. So that's your reactant. This is the reactant in the second one. So that's 2 lithiums plus, it's going to be I2, and the product is going to be 2 lithiums plus 1 plus 2i minus 1. The E0 cell is going to be the reduction potential minus oxidation potential. So it's going to be 0.54. That's the reduction. Gaining electrons, oxidation potential minus the oxidation potential. So that's minus 3.04 volts. And that gives you 3.58 volts, which is a very high voltage, 3.58. Okay, is this clear?
Yeah.
Yes, sir.
So let's continue tomorrow. We'll just do some more questions. It's a big worksheet. You can keep on practicing. How many papers did we? So we did 7, 8. So we're going to work out some more questions tomorrow then, okay? Let's continue tomorrow. Okay, Allah Hafiz. ये करते हो on